All right, I think we are good to go here. Thanks for joining us. This is Safe and Scroll up here. We'll be talking about user experience benefits from a unified multi-chain key store. I'm Daniel Helm. I'm from Scroll. I lead the developer experience team there.
And I'm Greg, tech lead at Safe on the network team.
And we've kind of have a demo here for you today, and I'm going to give some intro context. So cross-chain smart accounts are difficult to use. Right, in this world of EOAs, we have the user, their key, the verification logic, their assets. It's all bundled together into an EOA account. You know, your smart wallet accounts work differently. But this is how it works in an EOA. It all just kind of like lives and is defined by the protocol. When we get into smart accounts, right, we get to decouple the user from the verification logic and the assets that they hold. So we have a smart contract that it helps us, you know, bring in all sorts of fun new stuff. We can start thinking about spending policies, roles, social recovery, gas abstraction, right? This is an exciting world and why we're all here at Safecon. But there's a difficulty, right? And that has to do with key updates. So we have a user, they have a verification key A, and the logic on chain is expecting key A, and as long as that passes, you know, that user is going to be able to use those funds, use those assets. But, you know, they can update it to B, and now they don't have to use the same private key, right? We can do key rotation, we can do social recovery, but still we have this idea of a verification key that the user uses to authenticate themselves to the smart contract. Great. Where this starts getting hairy, though, right, is this user, now that we've decoupled the user from the wallet, from the account, this user has lots of smart contracts, and if they update one, that doesn't necessarily mean they're going to be updating the verification logic on the other one. So in this diagram here, user has now key B that they want, and it only applies to one of the contracts, and that is going to maybe be a bad UX experience. Okay, so for devs in the room, you say this is very easy to solve. We have these interoperable smart contracts. The whole thing here is that we can just go reference somewhere else, and that other place can be the thing that holds the verification logic against that key. And we can, you know, reference that. We can use proxies in our smart contracts and just point to that logic, and we're good to go. But this maybe doesn't work when we start going cross-chain, right? This user doesn't just have accounts on Scroll. They have accounts on Optimism. They haven't made an account yet on Arbitrum, but they have funds there already because someone just sent it to that address. And it starts getting messy, right? We want to do these key updates in a way where I make one transaction, I update a key, and that's true across the entirety of the ecosystem. So that's why we're exploring what we call the Keystore. Keystore was first kind of popularized by Vitalik in a series of blog posts from last year. And the idea, right, is that, okay, then let's just have all of these chains reference one centralized location where the verification logic against these keys works for these users. But there's a lot of technical challenges involved when you start working cross-chain, right? So there's trade-offs for how we implement this and how we think about it. And you can see in Vitalik's diagram here, we have this trade-off about the cost to users for doing these updates, using these keys, and the trade-off work required, right? And so this is using all these different types of fancy proof systems, whether it's Merkle proofs or ZK ones. But there's an outlier down here, right? If these layers can directly read from a key store on L1, we have something that is at low cost for a user and doesn't require wallets and applications to have to start thinking about ZK proofs and circuits and all these complex things. So I'll probably go more in depth to this at a talk later, but the Scroll solution here is, okay, let's have L1 still be where the key store is located. All these chains can like read from that as a source of truth, but in order to lower the transaction costs, so you don't have to always be updating things on L1, you can delegate to a different L2, which can then update those keys, right? And so that way the user gets the benefits of L2 costs while we still get the developer experience of putting all these keys on L1. And right, it doesn't have to be delegated to Scroll, it can be delegated to any of these options. And if you don't want to delegate, you don't have to. You can always interact directly with that if you prefer the censorship resistance and liveness guarantees that Ethereum gives you. So Scroll as first steps to implementing this, we have like proposals for our Keystore, but the thing that is actually really important there, right, is this directly reading from the Keystore on L1. Like that is the thing that we have to implement at the infrastructure layer. We can't ask Safe to do that. We can't ask these wallet providers to do that. And so we have a new opcode and precompile that we're hoping to get adoption from other L2 players called L1 S-load, right? This lets you directly read from L1's state. The idea is that we have trustlessly relayed state from L1. We can, verify these things with ZK proofs. When, in scroll, as we load this thing in, we are able to, in the ZK proof, make the proof in the infrastructure that this was the case for the state on L1, and so that no one else has to worry about that, making it really easy to implement for developers. You just say, I want to read this location on L1, and that's it. And also by doing this as a precompile, you reduce the verification costs per transaction. So when I use my smart account and I want to do something special, I don't have to go provide a bunch of Merkle paths and then verify something against that. I just say, go read it off of L1. So again, we're hoping to introduce a roll-up improvement proposal about this soon. But the idea is that we want this really easy for devs to use. We like to focus on developer experience. Give it the block number on L1, give it the contract address and the storage key, and you'll get that location directly in your smart contract on your L2. And so we've been working with a lot of people to try and get feedback here, and we had a nice collaboration with Safe, where they said, we can use this, and the rest of this is talking about the demo that we were able to build using this precompile. So.
Awesome. Thank you, Daniel, for introducing the Keystore and all the work you put together with L1 S-load. So I just want to demonstrate some kind of experimentation we put together for the Keystore with Safe, leveraging the L1 S-load. So basically, we put in place a module and a guard to delegate ownership verification from a Safe on L2 to a Safe on L1, and also disable the verification on the Safe of L2. So the high-level architecture of this thing is we have a Safe on L2 where we enable a Keystore module. This Keystore module actually behave just like a Safe in terms of multi-signature checks and validation, but instead of reading the owners and the threshold from the Safe on L2, it actually read the owners and the threshold on the Safe on the layer 1, which is the Safe Keystore at the bottom. So basically, a user can execute a transaction against the module. It's very similar to a traditional exec transaction function on Safe, but it will delegate verification to the Safe Keystore. And the second things we put together is a guard, because we don't want to sync signers keys to many Safe on many layer 2. We want the Safe Keystore on layer 1 to be actually the single source of truth. So what we do here, we kind of disable with a guard the capacity to execute transaction with the local state of the Safe. I'm gonna go into some details to show how this is working, and then I'll do a demo. In details, 2 steps. The first one is it just works like any other Safe module. So you need to basically on your Safe on L2, you need to enable the module, the Keystore module. And once this is done, you need to register your Keystore. So this is the address of your Safe on L1. What this is doing is just store the Keystore address on the module, and this will also enable the guard, so the guard to restrict access to the local state of the Safe on L2 in the at the same time. So maybe I can show a little bit of code here. Let's put this bigger. So this part, registration, is really straightforward. As I said, once we enable the module, we can actually store the key store for a given safe, and we set the guard to restrict the access of the safe on L2 and now use only the safe on L1 as a source of truth. So that's the registration part. More interesting part is the execution part. As I mentioned, it's actually behaving just like a safe. The safe keystore module behaves just like a safe. We get a unique transaction hash. We sign the hash, but we sign the hash with the key that is registered on the keystore and not on the safe. So we sign this transaction hash, and then we execute the transaction against the keystore. And what the keystore module is doing is get the keystore address from the safe, and this is where the magic happens, where we will actually leverage the scroll L1S load precompile to read the state of safe on a layer 1 from layer 2. And once we've got this data, the owners and the threshold, we can check the signature against this data. And if this is all good, we can just execute the transaction, and we've been able to move, move funds or whatsoever from a safe on L2, but with a verification that lives on a safe on L1. Maybe I can go to the code as well here, very quick. Put that. So we've got this execute transaction. Again, this is very, very similar to the exec transaction on a safe. We get the key store address, and what's the important part is we don't want to read the data from the safe on L2, we want to read the data from the safe on L1. And for example, for the threshold, we will just go here, and then we have this very simple function where we can do a static call to the precompile. We just need to pass, because we can get the state for any blocks, so we just need to pass the last block on the layer 1, the contract address, which is a key store on layer 1, and the storage key, to identify the owner or the threshold. I mean, the data we want to retrieve from layer 1. And once we've got this information, so we're doing this for threshold, we're doing the same thing for owners. Again, we get the transaction hash, we check the signature. Again, we recover the signature for this message against the owner of the safe on L1, and if it's all good, we can just execute the transaction and move funds or whatsoever. And yeah, just to prevent replay, we have this non-safe. I'm just gonna go fast now. So that's a part of the execution. Very quickly, we have this way to prevent the safe, normal safe, traditional path to run, because we want to use the safe on L1 as a single source of truth. So if you try to execute a transaction on the safe L2 from the normal path, it will just revert thanks to the guard, which do a pre-execution and fails. So demo time. All right. So we put together like a very basic UI. So I'm just gonna take a safe here. So I have a safe on L2. on my L2. And what we can see right now is the module is not registered. There is no Keystore register. So what I'm going to do is take a safe on Sepolia, which acts as a L1, where my MetaMask 2 and 3 are actually signer. And on this safe on the L2, my MetaMask 1 is actually the signer, and on L1, this is my MetaMask 2 and 3 that are signer. So one, oops, I need to connect MetaMask. There we go, MetaMask 1. So I'm doing enabling the module and configuring the module to say, hey, use this safe on L1 as a key store for this safe on L2. So it's good. So if I just refresh here, we can see that, yeah, my key store is registered. And now what I'm going to do is actually sign a transaction on behalf of the safe on L2, but sign a transaction with one of my signer on the L1 key store. So for example, this guy, MetaMask 2. So I'm just switching to MetaMask 2. All right. Disconnect. Connect. And when it's not working, and just start again. Okay. So now let's say I want to send some funds onto this guy. Let's say 0.01. So I sign the transaction with my Keystore signer, which is my MetaMask number 2. Okay, it's signed. Now I just submit the transaction. Okay, should take a few seconds to work. I'm doing the loader. Yes. There we go. So hopefully this balance should decrease when I refresh. And there we go. So we successfully move funds from a safe on L2, but with a verification happening on a safe on L1. And going back to the slide. Oops. Yeah. You can access the code of this demo on GitHub if you want. And I think this is it.
Yeah, next slide.
All right, we'll just have opportunity for just one question because we're behind schedule. Any questions? Yes, one.
Thank you. Thanks for the presentation. Talking about the L1S load, like how does it work? Like, is it taking care of copying the state to the L2, or what's there's like some ZK involved? How does it work?
Musical chairs up here. So how it works, right? So these L2s at this point are still like running centralized sequencers. Those are already running like archive nodes for L1. And so what happens is that they are able to call get proof against that storage slot. And then in the ZK verification that happens for that block that gets minted, it actually makes like a system transaction, which is a new type of transaction. It gets in the weeds, but in the ZK side of it, right, we already know our L1 state root. Now we have a proof against that L1 state root. We can like prove that in ZK, and then when we update our state back on L1 and provide a proof for that state transition, you know, that gets re-verified against the block number and the storage slot relative to the L1 state. So does that make sense?